Good morning all. This is a 3 to 4S flying capacitors balancing V1.4 for battery types NCM or LFP, and that's the size. So this is a cell balancing module using the flying capacitors technique, which is a green technique. Green because, or eco-friendly, because it doesn't use resistors to just burn away excess cell voltage. It actually redistributes it between cells by passing it into capacitors and then back into adjacent cells. So I like this because it's eco-friendly. So how does this work? Well, essentially it just sticks a capacitor across a cell, let's say between B- and B1, and then using switches, which are all these MOSFETs here, once that capacitor is charged up to the voltage of cell 1, it switches it so that it's placed across the voltage of cell 2, or placed across cell 2, and then if cell 2 was a little bit lower in voltage, a tiny transfer of energy comes out of the capacitor and into the lower voltage cell, and this happens continuously and I would imagine very quickly to transfer energy between cells to equalize their voltages. Now the technique can only transfer between adjacent cells, but of course that ripples down the line, and so eventually all the cells covered by this are equalized. So I don't want to babble on about this too much. I actually want to get it wired up. I'm going to put it on this 3-cell pack, 3S lithium ion pack. Now this works for both 3 and 4S because common configurations for lithium iron phosphate is 4 cells to get 12 volts. Quite common for NCM is 3 cells to get a rather poor 12 volts, nominal 11.1, as you can see there, but that's quite common. And they've implemented that using this diode. Oh, let's get in a bit closer. This diode, which I don't know whether you can see the pointy end, probably not yet. Right, the pointy end is pointing to B4. So if you only hook up a 3-cell pack, current can flow through into this end point down into the circuitry and fire this circuitry up. So let's just quickly go through what's on this board, as well as that diode. Those I think are polyfuses. I think that's what restricts this thing to 5 amps of operating current. We got sets of MOSFETs. I think they're in parallel pairs sitting next to each other, because I found that the gates were there's continuity between the gates. It's very difficult to check continuity on here because the whole thing is conformally coated and you have to break through the coating before you get a contact. So it's all very difficult to bleep out. I think there are 4 MOSFET driver circuits because you've got a chip, diode, capacitor, capacitor, and you've got that 4 times: chip, diode, capacitor, capacitor, chip, diode, capacitor, capacitor, chip, diode, capacitor, capacitor. So I think these are the gate drivers for these 4 sets of MOSFETs. There's a little SOT23 5-pin there, and I think that's the clever chip that does all the switching between, well, it may only be a biphase switch. It might just be move all the capacitors that way, then move them all this way. I don't actually know yet, but the run light is very near that chip, so I imagine that chip is driving the run light to tell you whether this is running or not. And then there's this little circuit here of 3 transistors, and as yet I'm not sure what that does, but I have a hunch. But I don't want to get too bogged down with the operation of this thing or the circuitry just yet. I mean, I will, because this thing is a very interesting device and I think it's going to be useful in my particular application. But what I want to do first is just get a socket wired onto probably just B-, B1, B2, B3, because this is a 3-cell pack. See if this thing fires up. Maybe take a look at some voltages, maybe take a look at some currents. Who knows? But let's just get it working. Right, JST plug, I guess that is, male, 4 pins for the 3S LiPo. I'm going to solder, these wires come with the balancer, and they're reasonably thick wires, probably just about rated for the 5 amps that this thing is rated for. Now this 5 amp rating is interesting. I believe that these polyfuses are rated at 5 amps, and that's what gives this a 5 amp limitation. But I doubt there's anything to stop this trying to shovel more than 5 amps if your cells are wildly out of balance. I think on the eBay listing for this it says that, well, let me have a look. Okay, on the 8S version of this, which I have now also ordered, 1 amp if there's a cell voltage difference of 0.1 volts, that's 100 millivolts, 3.5 amps at half a volt, and for 5.5 amps, which strictly speaking is over the rating of these fuses, I believe, I don't know what these are, they have just a V on them. Is that V for 5 in Roman numerals? Probably not. 5 amps, or 5.5 amps it says on this particular eBay listing, you'd need 1 volt of cell voltage difference between adjacent cells. Right, I'm going to solder the wires to these 4 pins. These tend to melt quite quickly and they will move around. So I'll put the corresponding plug in there. And that acts as a little bit of a heatsink, but also a physical holder to hold all these pins in place while I solder some short lengths of wire. I'm not going to make them long because I want to retain most of the length of this for when I use this somewhere else. I'll do that off camera. Nobody wants to watch me solder. Right, I've done that. So that should plug into this. Let's hope I've got the negative on the right end. Yep, seem to have. Black going to black there. So I'll just strip these back, solder them in there, and we'll fire the thing up. Right, that's all done. B- to the black, and we're running up to B3. Like I say, B3 will feed through that diode to power the circuitry. Now there's a little run LED on the back here. We're expecting to see that light up. There's also a run marking here, but that's a solder bridge. Now imagine you could put a switch on there so that you could remotely enable or disable this thing, but we shall see. Right, let's flip it over so that we can see the run light. Live power up, haven't rehearsed this. Let's see what happens. Oh, a little crack from here, and you'd expect that because there's a lot of capacitors on there, and that's running, so that should be equalizing these voltages. We might have to have a look at that in due course. Now what's interesting about this is that this first set of capacitors appears to be connected directly across these wire points. So I think what happened is, I mean, if you draw the theoretical circuit of this, you could get away with 3 capacitors and I think 3 sets of MOSFETs. There's obviously a lot more going on than that, and I think it's about impedance to the cell, to the battery pack. They probably couldn't get this thing to run efficiently by trying to transfer from cell to capacitor and back to cell. So actually what you've got here is 4 capacitors mimicking or copying the cell voltages, and they do transfers between, I think, probably these capacitors using these capacitors. I don't quite know why there are 5 here. It's a bit odd, that run light still on. So I believe they're doing it for low impedance purposes, simply to shift energy into the capacitors, and then that of course is mirrored on the pack eventually. Now this run light, it is my opinion, and this is only an opinion at the moment, that this stays on all the time, even when the pack is completely balanced. The only time this will go off is if a voltage detector, and that could be these 3 transistors, detects that the pack voltage is so low that there's a risk that this thing, and this thing has quite a high operating current, that this could drain the battery down to nothing. So this then goes into a lower power sleep mode. It probably stops the clock, stops the switching to the MOSFETs, shuts everything down as far as it can. But even then, there's still a reasonable operating current that this thing draws. And if you look at the eBay listings, they do say only use it on battery packs that have, oh, I can't remember, something like 60 amp hours or more. Oh, they're getting warm, actually. That's interesting. Yeah, those capacitors are getting warm. What about that one? Now, of course, that might just be heat coming up from the MOSFETs. They're not getting warm. Well, not as warm. Nothing's particularly warm under there, but the capacitors themselves are warm. Interesting. Now, I can't do much with this setup, but what I can do, I think, is monitor the pack voltage, not the individual cell voltages, but the pack voltage with this thing. Yeah, so we got, oh, that scared me. 11.08, so it's probably saying it's a bit low. That's fine. 11.1 nominal, that thing, isn't it? So let's plug that in and see how rapidly the voltage plunges down. 11.08, it's flashing alternately white and red. Right, that has dropped to 11.07/8. So yes, it is pulling some current. Now the only time I think that LED is going to go off is when this pack gets to a voltage, this thing times out, that's so low that this board tries to protect the pack from dropping to too low an overall voltage. That's what I believe. I don't think this light goes off when the cells are balanced. Just check the temperatures on these caps. It might have cooled down a bit. Okay, so we'll run a DVM across here and look at the cell voltages. Or of course I could pull that out and plug it into the balance port on here. And well, yes, they're all pretty similar. This is not a brilliant setup because what I really want to do is have the cell balancer on here at the same time as having the voltage monitor. How can I do that? Just going to change the low voltage alarm so that it doesn't keep bothering me. How about 10.5 volts? That should do it. Back. Yeah, so that symbol is no longer flashing. That's better. Still thinking about how to parallel this into there. I'm sort of thinking some of these on some strip board. I don't know. Right, I've done this. I've put a socket on there for the LiPo. Long wires to here because it's just measuring voltage. Short wires to here because of course it's handling current. So let's plug that in. See if it all works. In you go. Yeah, that works. I can now see the cell voltages. Now, of course, they may not look balanced because this thing may not agree. Well, of course, this thing isn't really measuring voltage. This thing is just flying the capacitors around and redistributing the energy such that the voltages end up the same. So it depends on the accuracy of this thing, really. We'll keep an eye on it. Oh, I don't really like the way the wires have all bent on the bottom of there. I'll get some hot glue on there, I think, to brace it all. Well, now, even with this, there really isn't much to see. That run light is on. No warmth there because all the cells are very similar voltages. Any discrepancy here is highly likely to be the measuring circuitry of this device, because this really can't be inaccurate because it's simply moving energy between cells based on their relative voltages, so it's got to be spot on, unless there are minute differences in on resistance of MOSFETs or things like that. You'd expect it to be precise. I think a setup where you can see absolutely everything that's going on would be more cells, a bigger balancer, a monitor to show all the voltages, mismatched cells to start with probably, but also the currents that are flowing through these wires. It would be a good thing to have an ammeter that has lots and lots of current readings all visible simultaneously. And I'm kind of thinking, because these are all at different potentials, I'm thinking the ACS 712 wouldn't be a bad idea because they're the current measurements are galvanically isolated from the voltage and signal parts, and then an Arduino with an OLED showing all the currents that are flowing through these wires. But that would take a fair amount of time to set up. Perhaps the only thing I'm really interested in here is how long it takes for this module to drain this battery, and this hasn't been charged for years, down to a point where this turns off the run light. So perhaps I'll leave this set up and just keep an eye on it and come back when the run light goes out. I may not catch it on video, almost certainly won't. Now this module says that it's suitable for NCM, nickel, cobalt, manganese, or LFP, lithium, ferro, or iron phosphate. So because it's suitable for LFP, you'd imagine that the cutoff would be at quite a low voltage, probably lower than you might want for NMC or LiPo. I can't see that this circuitry is doing anything in terms of measuring voltage on a per cell basis. It can only be measuring the overall pack voltage. There just isn't the circuitry on here for doing a per cell basis measurement. So I'm guessing it's just going to be a case of when the pack voltage gets down to a certain low point, this will shut off. This might all be a bit more visual if this were on supercapacitors, for example. Just been trying this bulb. I've clipped that onto the most negative. So if I put this across one cell, say cell 1, that thing keeps timing out. Cell 1. Okay, the bulb's on, you can't see it. The differential voltage just below the pack voltage climbs up as this is stressing the first cell. Immediately I take it off, that shoots straight back to that 14 or 15 millivolts that it's been on the whole time. So that, I presume, has to be the balancer that's doing that. I don't have any other ground points on here that I can really get to. Maybe I'll solder a ground point onto my... oh no, I've put hot glue on it now, haven't I? Now if I put this bulb across 2 cells, stay on. Right, there's the bulb, you can see it. Now the deviation just isn't happening because I think the balancer is able to pull it back or hold it in balance. So it just isn't deviating. If I do 1 cell, I think because the filament is so dim, that's able to pull it a considerable distance out of balance, 24 millivolts. Of course, a low temperature filament has a much lower resistance. The minute I remove that, straight back to the 13 or 14 or 15 millivolts that it's been showing. Yes, it's not a very good test, is it? And now I've got the 9 capacitor supercap bank charged up, voltages all pretty close to 2.7. The active balancer with a little switch on the run pins here, but there isn't enough voltage across the capacitors. I could try them in pairs, I suppose. Yeah, just not enough voltage for this thing to do anything. And now I've got the supercapacitors wired to this every 2 capacitors, and I've charged it to 17 volts. We're showing 2 volts per cell. Unfortunately, cell 2 is slow to come up. Now, cell 2 was the bad one before, so I swapped it with cell 9, capacitor 9. And in the process of swapping them, capacitor, what was 9 but is now 2, also seems to have gone bad, which is driving me up the wall, because this will not run. I switch it on with my little switch, and it will not run. So is this monitoring individual cell voltages, and it realizes that, well, it's actually cells 1 and 2, which is the first that this thing sees, and it's seeing both of them. That one's quite low in and of itself. This one is so low it's not showing up on there at all. I don't know what the minimum voltage of this thing is, but of course I'm well below what this is intended for, lithium iron phosphate and lithium nickel manganese cobalt. So I can't even get this to work. I'll have to think of something else, but for the moment. Right, this is working. I've now got my 6 supercapacitor bank. Can't really show that very well, but there it is, 6 supercapacitors. There's a voltmeter on there. I've taken it to 12 volts. That's 2 volts per capacitor. Those are the voltages. This now turns on when you put it in run mode, and that, presumably, at quite high current, is equalizing. This is strapped across pairs of capacitors so that it can see around about 4 volts on there. And it's balancing, but of course we've got to do this mathematically. So 2.14 and 1.75, is that about the same as 2.07 and 1.85 and 2.04 and 1.88? You do the math. Now what I really wanted to see was when this is in run mode, which is there, if I switch off the supply to the supercap, these voltages will fall away. Now there really isn't a load on here other than this this voltmeter, but that's extremely high resistance, and this circuit pulling energy out of these capacitors. Will they sync back quickly enough for us to see that run light go off when, well, either the pack voltage, which is, can we see it actually? Yes, I think we probably, oh no, that's on. I want to see the voltage. Oh, come on, I've got dodgy button syndrome. No, we can't see the voltage if that's not on, I don't think. But we can see the voltage on this meter, approximately, about 11.5 volts. But at a certain voltage, this should shut off. But it's just all not very satisfactory, is it? Because we're having to add voltages up here to see what they actually are. I haven't really got a load. I suppose I could put a load on there. Just 1 second. I have this bulb, but the other problem is if I breathe, everything is going to fall off the desk. So that's the other problem. Can I put that in there? Will it stay in there? Will it connect? Oh yeah. There it is. Oh, you can't see that because it's not in shot. This is about to slide off the desk because the 5th wire is not connected to anything, so that's dangling down. So I just want to see if that voltage goes low enough, does that run stop light go off? And I can see the voltage has got to about 9 volts. These are plummeting down quite quickly because of the 24 volt bulb. At some point, oh, the sun's in my eyes now. At some point, that run light should go off because this battery balancer has recognized that, well, either the pack voltage has dropped too low or an individual cell voltage has dropped too low. But it's still on at the moment. Will this little yellow LED go out? Oh, it is going out. It's fading out. It's gone off. So yes, at a certain voltage, this is around 7.5 volts, and this is seeing that whole pack voltage. Now that's 3 cells. Yeah, this has gone off. So what's that? What is this darting about? What's that per cell? Possibly because this is cutting in and out. 7.5, 9 would be 3 volts per cell as far as this is concerned. 7.5 is 2.5. Yeah, that's now going flaky because it doesn't like these low voltages. Yes, I think this looked like it cut out at about 2.5 volts per cell, which is about what you'd expect for a lithium iron phosphate stroke NMC balancer. That's all I can do today. That's all I think I can manage. I need a better setup. Right, finally, I think I've got it. Oh, you can't see that very well. But anyway, that's just for me to check all 6 capacitor voltages to make sure they're not drifting too far out of bonk. 12 volts coming in across the capacitors, that's nominally 2 volts per capacitor. Now this is looking at them as pairs of capacitors, and you can see that they are wonderfully balanced. 3.92 volts, and that's because the balancer is on, balancing them at 3.92 volts. Now that's 3.92 volts per pair of supercapacitors. So there are 3 pairs because this board has 6 supercapacitors. So the balancer is doing an absolutely wonderful job of balancing. Now if I turn off the power supply, the voltage on the supercaps will go down. I'll just check this to make sure that nothing's too high. One of them's 2.2 and its neighbour is 1.6, but it doesn't really matter. They're acting as pairs, and you can see as the voltage falls, the balancer is still balancing. It's got 3.87 across the board, 3.86 across the board, 3.85. So they're all tracking down together, the 3 pairs of supercaps, behaving as cells that this thing will understand the voltages of. This thing behaves itself. This is actually quite good at working with these very low cell voltages. Just can't see that, can you? Cell 1 is 2.1 and cell 2 is 1.6. In terms of the pairs, they're miles out of bonk within that pair, but the balancer is bringing them as pairs into wonderful balance. 3.77, 3.76. They're almost moving together. 3.75. They all moved absolutely together. Didn't that time. 3.74. Now at some point this will say, that's no good. That's not high enough for it to be called a lithium iron phosphate battery. And this will stop running. But the voltage would have to get down to something like, well, it was 2.5 volts, wasn't it? I think we said. So I'm just watching to see when the balancer stops running, and we're down to 3.02 volts per cell or capacitor pair. Will it drop out at 3 volts? I seem to remember it dropped out at about 2.5, so I'm not expecting it to stop running yet. 3.0 volts across the board. Certainly seems to be working less hard to balance, but it's hard to tell because I don't know what's accurate here and what isn't. But that's still running at 2.99 per cell. Well, I think that dropped out at about 2.65 volts per cell. So I've just turned on the power supply. This is coming back up. There's quite a lot of hysteresis on this. It doesn't cut back in until the cells get a fair bit higher. I was just wondering actually if these 3 devices here are TL431s maybe, but then it really should be looking at all 4 cells, shouldn't he? Not just 3 cells. So maybe not. That's come back on at pretty much bang on 3 volts on one of them. Now of course it's balancing them because they had drifted a bit, and it's pulling them in pretty well. 3.16, 1718, 19. It's within 10 millivolts now. Yeah, and it's pulled them all in. Turn this back off. That's how to turn it off. And just watch again when this drops out, at what cell voltage this drops out. But I think it was about 2.65. But I'll watch it again, try and catch it, because I missed it last time. Right, 2.74 on here. The yellow light is still on. Determined to capture this visually and on camera. 2.73. At some point this will complain. It'll just say, I'm not getting sensible voltages, they're completely silly, because they're down at like 1.5 volts. That's dropped out to all zeros. Yes, it's complained, and that went off absolutely at that instant. 2.68, something like that. Yeah, I don't know why it corresponded exactly to that. Maybe this suddenly pulled a burst of current or something. But yeah, about 2.68 volts. This drops out, but doesn't cut back in until 3. Oh, it was around 3.0, wasn't it? Okay, that's the voltage parameters of this thing going into run and stop mode. in another video I will have to look at what this is capable of in terms of currents. That's much more interesting to me. But for this video, that's it. Cheerio.